the difference between an exponential function and a power function? Can you provide me an example at all, or? We always think of powers and exponents as kind of the same thing, don't we? But our job today is to differentiate between the two. How do we take and differentiate between a power function and an exponential function? Okay, kids, what was the general formula for exponential functions?
P equals P of O, A to the T.
A to the T power. Was our exponent a number or a variable?
It was a variable.
Okay, so the big difference today is this. Instead of our exponent for functions being some kind of a variable, our functions are going to be what's known as a power function. So the power is going to be some number that we're going to work with today. So let's just kind of make sure we understand the difference here. I'm going to put two functions up here. Function number 1, maybe y equals 2 to the x. Function number 2, y equals x to the second. Okay, which function is my exponential function? Y equals 2 to the x, okay? Because the exponent is a variable, making y equal x squared. What type of a function? Power function, okay? It's a power function because the exponent is a what?
Constant.
Yep. I like the way you put that. That was good, Noah. Okay, so today, guys, dealing with power functions, our question is, how are power functions manipulated, and how do they relate to real-life situations? Okay, volunteer to read my goals for me then, in terms of how are power functions manipulated and how do they relate to real-life situations. Who wants to read those goals for me? Who's got it first?
I will.
Go for it.
Write and evaluate power functions.
Okay, we're going to look at writing some power functions and evaluating them. Okay, next one then says use power functions to model some real-life situations. And then this is going to become kind of a theme that we talk about a lot right here. Determine which functions dominate over time. Okay. Now, dominate just means that over time, which function has a higher y value over time. Okay, and we'll talk about that. But also, I want to tell you this today too. For some of these dominant functions that we're going to talk about, we might want to look at some properties of Desmos for us today to see what's going on there. So you may want to jump into Desmos at some point today. I'm not going to tell you you absolutely have to, but it might be beneficial for you when we go through the assignment. Okay? All right, so vocab. Let's take care of our vocab first today. Power function. Power function is any function where y equals some constant k times x to the n, where k and n are any real constant numbers. An example might be y equals, I don't know, 2x to the 5th. Okay? That would be an example right there of a power function. Again, what power or what degree is this function? Fifth power. Okay? Zero power. Okay? Zero power says there's a zero exponent rule. It says a to the 0 is equal to what? As long as a does not equal 0. This says that anything raised to the 0 power is 1, where a does not equal, this should be 0 right there. Okay? Anybody know why stuff to the 0 power is equal to 1? Let me ask this question. What's 6 divided by 6? So what's 6 to the 4th divided by 6 to the 4th?
1.
Right? Yeah, since these bases are the same, what do the 4s really do to each other? Well, they don't really cancel each other. They do cancel each other out, but it would be like 6 to the what power again, kids?
0.
Yeah, that 4 minus 4, you subtract if you have like bases in division, you subtract your exponents to see what your new exponent would be. That's why stuff to the 0 power is equal to 1. Okay. All right, negative integral powers. A negative exponent means how many times to divide by the number. As an example, 8 to the negative 1 is equal to 1 divided by 8 to really what power, kids? Okay, you've done this before. If I say, hey, kids, I have 4 to the negative 3 power. Anybody know what that equals right there? Where's 64 coming from? Yep, this is exactly right. This is the same as 1 over 4 to the third power. And we can evaluate 4 to the third power. It'll simply be 1 over 64. So I think that, understand this. If you have a negative exponent, this was like a fraction bar down here. Anytime you have a negative exponent, the base can be moved to the other side, making that exponent turn from negative to positive like this. So if you just move stuff to the other side of a fraction bar, in terms of negative exponents, that's how you can make them go away. All right? You've talked about fractional powers before. A fractional exponent is an alternate notation for expressing powers and roots together. So as an example, I like this one right here. 27 to maybe the 2/3 power. What's true about my exponent there? Whole number or not? Not a whole, but it's still some constant. It's a power. Anybody know how to write that as a root?
3 over 2.
Close. Anybody know what this equals? Maybe that's a better question first. Okay, what if I told you this? Anytime you have some kind of fractional exponent right here, this is the same as saying, well, let me give you the rule. Suppose you have x to the a over b power. This is equal to the b root of x all to the a power, like that. Okay, so this would be what root of 27 first? This would be the cube root of 27 all to what power, kids? Okay, and yeah, the cube root of 27 is 3, and then that 3 squared would become, yeah, value 9 there. Okay? Okay, we did that a little bit last year in Caltrep. I don't know if you recall all that. But in fact, funny part, guess what? They're working on it right now in Caltrep.
Yeah, I heard in the, they're talking about radicals, and in one of the videos you took, they could hear me talking about radicals. So they still talk.
That's good. If you're talking, it's probably a pretty intelligent conversation.
No, Sophie and I were actually discussing writing a rap about radicals, and we were rapping about it.
We were writing a rap. Sweet. We're talking about radicals now and talking about rapping it again, and we're recording it.
Yeah, this is like the sequel.
All right, even functions. Let's talk about even functions. It says a function f is even if the graph of f is symmetric with respect to what? You might want to underline that, okay? It's going to be even if it's symmetric with the y-axis. It says algebraically, f is even if and only if f of negative x equals f of x for all x in the domain of f. What this is really saying, I'm just going to pick on f of x equals x squared. Is that okay? You guys agree that that's a parabola with a vertex at the origin, right? Is a parabola with a vertex at the origin, or a vertex for that matter on the y-axis, is that going to be symmetric about the y-axis? In other words, will the left half fold over the right half? Okay. So that would be considered an even function. And I can say that this is an even function because, kids, watch this. F of x was equal to what in the beginning, kids?
X squared.
So I can say f of x was originally x squared. Guys, what if I replace the positive x with a negative x? What they're really saying is replace this x right here with a negative x and square it. But what would negative x times negative x equal on the end again? Positive x squared. So are f of x and f of negative x equal in this case right here? So if they're equal to each other, then algebraically that's what it means to have an even function. And we'll talk more about examples like that as we get through the notes here, okay? But just really the two keys about f of x has to equal f of negative x in order for it to be even. That's how you would show it algebraically. Graphically, symmetric about what? The y-axis, okay? Now we talk about odd functions, and probably the easiest odd function to talk about is f of x equals x to the third power. Okay, now this one's a little trickier, but a function is considered odd if the graph of f is symmetric with respect to the what? Meaning if I make half a turn at the origin, if the origin is my center of rotation, the graph would look exactly the same. So maybe, I don't know. I did a drawing it. The graph of x to the third might look like this.
Oh, I see.
Okay? If I would take and say, all right, it passes through the origin. If I would spin that halfway around, do I have the same graph? Or if I would make half a turn, would I have the same graph? The answer would be what? Yes. Okay? Now, the part that's maybe a little more difficult with this is right here.
Please release the boys JV and fresh soft basketball team at this time and the managers. JV, fresh soft basketball boys teams and managers.
This says, in this case, a function's odd if f of negative x equals negative f of x. Okay? So right here, kids, let's talk about f of negative x. In other words, negative x to what power? So you would have negative x times negative x times negative x. Let's see, three negatives times themselves is going to be what? Negative x to the, Okay? But we also need to show that that's equal to negative f of x. Well, kids, negative f of x was equal to what power originally here? X to the third. But if I negate the whole thing, that equals what? Are they the same? So if those turn out the same, then it's considered what type of a function? An odd function there. Okay. All right, dominant functions then. And it says, when considering functions made up of the sums, and this goes on to the next page, doesn't it, kids? And I should have moved that all onto the next page, but it says, what's that?
Ours are all on the, is all on the.
Okay, so somebody read that first part that's up here. When
Considering functions made up of the sums.
differences, products or quotients of different sorts of functions. In other words, you have polynomial functions, exponentials, logarithm functions that we haven't talked about yet, or different powers of the same sort of function. We say that one function dominates the other. This means that as x approaches infinity or what?
Negative infinity.
The graph will eventually look like the dominating function. Okay? Dominance looks like this. Let's just say I have a graph that I'll draw. You might just want to sketch this right here. Okay? Maybe I have a linear function that starts out like this. Okay? And maybe this is like a value of 2. I don't know what it is. All right? And then let's suppose that I have another function that starts right here and finally catches up right here. Between 0 and 2, let's just pretend one function's linear and the blue one is exponential growth. Those are things we've talked about, right? Between 0 and 2, which function is dominant? The linear one or the exponential one? In other words, which one has higher values in that window from 0 to 2? The linear one does. But what happens at 2? The exponential catches up, okay? So right here, this exponential function catches up, and from everywhere on, like these dotted lines, at 2, which function finally starts to dominate? Well, you would say the what? Exponential function. So dominance just means which function is going to have a higher y value as x is doing what, kids? Increasing, okay? So in here, I don't know what I put up here. What was...
Exponentials, dominant, polynomial.
Okay, so any exponential function is going to dominate a polynomial function. A polynomial function pretty much is the sum or difference of different power functions. So as an example, I don't know. Maybe you've got 10 to the x power. This would dominate maybe 3x to the 70th power plus 2x squared. That would be an example right there. Okay, that would be an example. It says that polynomial functions dominate what?
Logarithms.
So you might have the 3x to the 70th, which is a polynomial function plus 2x squared again. Might dominate the log of, I don't know, 2x to the 90th, something like that. Okay? It says among exponentials, larger bases dominate what? So if I have 6 to the 2x and 4 to the x right here, which one's going to dominate? higher
Base.
higher base. Okay, they're both exponential, so the one with the higher base. It's the higher base, not necessarily the higher exponent in terms of the variable, but the higher base. It says among polynomials, higher powers dominate. So if I had maybe 2x to the 7th and 14x squared, which function over time is going to dominate? 2x to the 7th would dominate 14x squared. Again, it's just basically one function is eventually going to pass another. It might start out behind that function, but over time, as the x values get very, very large, it's going to catch up to another one and then overtake it. Okay? It's kind of like New England Patriots in football. For years, the Patriots used to be bad. They were getting dominated. Then along comes who?
His name starts with B.
Tom Brady, right?
I was going to say the coach, but sure.
Belichick. Along come Belichick. Okay? You can say that too. All of a sudden, there was a turning point, and all of a sudden the Patriots were winning all the time. That's kind of what happened right there. They took over. They started out slow, then took over. Okay? All right. Are you guys good on terms right now? That's my first question. Okay. Let's get through example 1, see how far we can get on this today. Guys, simplifying the following expressions. That's our first thing that we need to know how to do. We talked about this idea of having fractional and negative exponents here, and we need to evaluate some of these, okay? So guys, 27 to the 4/3 power. Anybody want to tell me how to write that in radical form? What root of 27 am I looking for first?
Cube root.
Okay, so we're really looking for the cube root. We always put the denominator part out here as the root, or the index, if you will. So we're looking for the third root of 27, and then we're going to take that answer to what power?
4.
Okay, let's evaluate, kids. Help me out. Anybody know the third root of 27? 3. Now we're going to take 3 to the 4th. 80 how much? 81. You bet. So this becomes 3 to the 4th power down here, which you bet. That's 81. Okay. Give you guys a second. See what you come up with there. I'm going to get a cup of water here. By the time I get back, see if you have those. Be careful on that second one, because that says 8 to what power?
Negative first. All right, 8 to the negative 1/3. Anybody want to take a shot at it?
1/2.
1/2, you bet. I don't know how you started this. Kylie, why don't you talk me through this quickly?
Alright, so I wrote out cube root of 8
Okay.
and all that to the negative 1 power. And the cube root of 8 is 2.
Okay.
And that's to the negative 1st power. And then you just flip her over the line.
So it's like 1 over 2. Very good. I did mine a little differently. I called this, I called it 1 over 8 to the positive 1/3 right off the bat, which meant 1 over the cube root of 8, right? But either way, where do we end up at? 1/2. Excellent. Okay. Anybody have the next one?
10,000.
10,000. Okay. Kind of a giveaway, wasn't it? How many zeros are in here? If I'm looking for the 5th root of 100,000, what is that value? And then this really becomes 10 to the what?
4.
Yeah, this becomes 10 to the 4th power, which is like a 1 followed by how many zeros, kids?
4.
What if that would have been 100,000 to the 2/5 power? What would it have been then? 100, you bet. Okay. You guys feeling good about simplifying expressions with rational exponents? Are you able to make the connection of rational exponents and put it in terms of root form or radical form? All right, excellent. Let's talk. I like these next problems here. It says determine which function dominates as, and this should say x approaches infinity, okay? It says, is 2 times 4 to the x or 2x to the 4th going to dominate?
2 times 4.
Why are you saying that?
Because that one is an exponential and not a polynomial.
Okay, so exponential functions are going to dominate basically everything. So you're going to take the exponential because exponential functions dominate. What type of function is this?
Polynomial.
You bet. Exponential functions my friends, will dominate exponential functions dominate power functions. And again, I'm gonna make a visual of this here quickly. I'm gonna make a visual of this. You guys have those two functions ready for me. I'll wait till I know everybody has that down. Anybody need more time with that up there? Good, Cade? Kylie, Bell, you guys good? Noah, good? Okay. I'm going to jump into decimals again quickly. You guys, I don't know what the functions are, so let me pull this up here. Okay, I think the first one was 2 times, was it 4 to the x, kids?
Yes.
Oops, I didn't want to do that. I need to raise it to a power. There we go. And then what was the other one?
2x to the 4th.
2x to the 4th? Okay, if we look at this just in terms of x going towards infinity, looking at positive values here, kids, what functions already appears to be dominating?
The red one.
The red one, okay? Now I'm going to zoom out a little bit here. Change this down here. You guys remember how to change your x and y values? If you click on this here, you can hit shift and change that to blue and then stretch stuff out or pinch it like that. It's getting pinched quite a bit.
You press the home button. Does most of these have a scroll function?
I could press the home button, couldn't I? Okay. A little concerned about this one. This one here appears to,
Oh, there we go.
but that shouldn't happen, should it? Is that red function ever going to catch up again? Doesn't look like it, does it? Has to, though. Wow, we picked a good one. Let's do this. Let's change our window this way. Somebody punch in 100 to the 4th power for me.
Got it, baby?
Got that number?
It's big.
1 billion?
I think it's 100 million.
100 million, so I'm gonna say this is 200 million. Holy smokes. This would be 200 million at x equal 100, right? So let me get some y values in here. See what 4 to the 100 power is. That's gonna be a really big number.
Let's just say it's times 10 to the 60th.
I'm gonna go to a billion then, okay?
Red catches up. There it is.
They do catch up, doesn't it? Okay, see it? All right, you just gotta mess with the windows a little bit. So, yeah, it was kind of confusing at first, wasn't it? It's like, wait a minute. Looked like I was lying, but the red one does catch up and dominate right here, right?
Eventually.
Okay. So, you might have to play around with windows a little bit to see that over time, that that's gonna happen that way, okay? Wow, interesting. If I go back to the notes here then, kids, what type of function is this one that we circled?
It's exponential.
Exponential will eventually dominate the power function, okay? So, we also want to talk about some end behavior of things here. You know, and right here, I think that, I think what we'll do is we'll get this example done, and then we'll kind of stop there and pick the rest of this up tomorrow. But it says determine what happens to the value of the function when x approaches infinity and x approaches negative infinity. What's our function right here, kids?
Y equals 1/2 x to the 4th plus 9.
Okay, first of all, is the degree of that function odd or even? Even. So is this going to make like an S-shaped graph or something more like a U-shaped graph? Let's just confirm that real quickly, okay? So I'm going to zoom home. I'm going to get rid of this. I'm going to get rid of this. What was that function again? 0.5x to the
4th
Yeah.
plus 9.
plus 9?
Yeah.
Yeah, because the even ones are U-shaped, like
Guys, that's exactly what we get as a U-shape. So here's the deal. When we start talking end behaviors again, as my x values get really large to the right, where's my graph going? Is y going towards positive infinity or negative infinity as we move right then?
Positive.
Likewise, moving left. If you move left here towards negative infinity, what's happening here?
Positive.
Yeah, so what I would probably choose to say here, kids, is the following. I would say as x approaches positive infinity or moves to the right, then our function y approaches what? Positive infinity. And likewise, when we were moving left on the graph, as x was approaching negative infinity, as x approaches negative infinity, where is y tending towards? Positive infinity again. So you're always going to be asked about end behaviors like this. They're going to say, what characteristics do your graph have as x approaches both positive and negative infinity? Typically, not always, but typically, if you have an even function like this, this is what will happen. What do you suppose would have happened if this leading coefficient, 0.5, was negative? Instead of like a U shape, you'd have had,
an upside down.
yeah, and everything would have approached what then?
Negative.
Negative infinity. Okay, so I think you can handle that part there. All right? Okay, questions up on the first 2 pages so far. How are we doing? Let me see what's on the next page here. I think,
Some empty boxes.
yeah, I think I want to wait on this right here. I'm going to hold off on this until tomorrow. This is going to take a little bit of time to get through. I know we've got a few real life applications, so I'm going to stop this right here.